So I'm going to present a quick overview of what we've been doing at AdaCore in our technological stack that can be interesting in the academic world. So first, starting with the evolution of Ada, the language that we all love and use. So Ada 22 has gotten the final stamp of approval by ISO this year, but we'll continue calling it Ada 22. And so it's available now with GNAT, with a switch GNAT22 to set the default language for the code that you're compiling. Because the actual default, if you don't pass the switch, is the previous version of Ada, so 2012. And I presented last year the various evolutions of Ada 2022 that are supported in GNAT, and mostly that excludes the parallel features that Miguel spoke about, at least for now. But we're already looking beyond Ada 2022, so with extensions and two sets of extensions. So that's a change we've done this year. We've separated the extensions to Ada in two groups. One set of what we call curated extensions that are better supported, that are ready for use under the switch GNAT-X, and more experimental extensions that are still evolving and where we'd like to get user feedback, and that are available with GNAT-X0. And so in more details, so regarding these curated extensions, so some of them are already implemented in the current version of the FSF toolchain that you get, for example, with Elia or directly downloading from the website. So two that I talked about last year are this fixed lower bound for arrays. So you can set the lower bound of this string subtype starting from 1. And you can use generally the object notation even if the object C here is not of a tag type. So provided increment is a primitive operation. So that was already available. And for the next upcoming version of the FSF release that should be available soon, so I hope Fabien will talk about it, we have new features like this conditional when construct. So you probably already know that exit statements in Ada can have this when condition appended to the exit statement to state when it exits. So there's the same now for return statements, raise statements, and goto statements. So you can do return when condition, for example. We have pattern matching now in this extension of Ada. So pattern matching is uses the syntax of case statements, but case statements in Ada are only for now on discrete types. With this pattern matching extension, you can use that on structured types or records and arrays. And so, for example, here we can switch on a record that has F1 and F2 components of, say, an integer type, and select for the first branch the case where both are positive. A final one, which is quite nice, taken from languages like Python and Rust and many others who implement this nice extension, is string interpolation. So instead of concatenating yourself strings that you get from printing values, you can simply use the expression of a certain type, provided there's a corresponding put string function. And then using this syntax F quotes, so that's the F strings that we took from other languages, you can put in curly braces this expression, and the corresponding put string function will be called on the expression. And of course, the compiler will check that the expression is well formed semantically. For all these, you can look at the GNAT reference manual. And so I won't mention it more, but I put here in the slides the reference to the corresponding section. Now looking at experimental extensions under this other switch, there are simpler accessibility rules so that you don't get bitten anymore by dynamic accessibility rules, which can be quite complex in Ada. So it's more restrictive, but essentially the compiler protects you. There's this Pragma storage model. So that's a replacement for storage pool that allows you to manipulate memory through pointers, even if it's not the native memory of your computer. For example, memory in the GPU, so you can allocate, deallocate, move values from the native to the CPU, to the GPU and back. And the last one is this thing that is very surprising to people who have been doing Ada for a long time, is the ability to declare local variables outside of a declare block. So here, after this statement, which increases x, I can declare a new variable, square, directly within the single sequence of statements. So for all these, same, you can look at the GNAT reference manual. And now for future evolution of Ada and Spark, we have various extensions that we're looking at, in particular in the context of this GitHub project that I put at the end, where the first three are targeting embedded developments. So the ability to have tag types for which we know the maximal size statically, so that we can treat them as constrained objects. So use that for the type of a component, for example. Same for indefinite arrays, so where we would have maximal size allocated, provided you use this with definite aspect. And the final one, which is the ability to create values dynamically, well, at compile time when you load a file which contains the actual bytes of the objects. A last one, which is not particularly targeted at embedded, is getting generic instantiation which are structural, so that you can have equal generic instantiations based on the arguments. Now we're looking at Spark evolution. What you have already in the coming version of Spark with FSF 13 is nice usability improvements. So the ability to call GNATpuzz, so the main Spark tool analysis tool, simply with the switches on the files that you're interested in without project file. So either it will find the current project file or create one if there's none. So that's quite convenient for demos or coursework. Now Spark can call all the provers on a single formula, so verification condition, or VC for short. Previously, it was calling provers in sequence on such formulas. Now it can call them all in parallel on every single formula and just stop when one of the provers terminates with the answer. More counterexamples are checked before being displayed. So we improved the way that counterexamples are checked so that we only issue valid counterexample when the proof doesn't go through. And we have completed this verification now so that you have more chances of getting this counterexample, which are quite useful, especially when you learn proof. And finally, there's now a detailed list of assumptions whenever you do proof. Please look at the user guide for the exact lists. We did a lot of work, and that's very useful in the context of certification, but that would also be useful in terms of teaching to show the boundary of what you do when you do formal verification. We have improved the Spark standard library. So previously, some of these bits were in the GNAT standard library, and some were in what we call the Spark lemma library. Now, these units are available both in the full runtime and for the bare metal or light runtimes. So you have now the infinite precision integers and rationals, same as in Ada. So under this Spark hierarchy, that's quite convenient for either teaching or for modeling properties, like we saw with Rani's presentation. We have functional containers and formal containers, which are expanded. So in functional containers, so those used for specification, we have added infinite sequences using these big integers for the length of the sequence and multisets. And for formal containers, we have completed the set of containers with two hierarchies of bounded containers. So these bounded containers, they are definite for definite objects, and the containers themselves are not controlled. So you can use them with a light runtime, for example, on bare metal. While the unbounded containers, well, you can grow them as you want, but they are indefinite. They do dynamic allocation, and they are controlled precisely because we do dynamic allocation. So we want to deallocate when the container exits its scope. We still have the lemmas like before, and something to answer Rani about the by operation that you find in Y3 or Daphne or other proof-centric languages. So we have now a unit called cut operations, which is precisely for helping the proof in a reduced context in an expression with these by and so functions that are interpreted spatially by GNATproof. And on top of that, so we have added contracts for I/O in the standard library, so in particular all the I/O and the string standard library. What's coming next? So it's done already in the development branch, but due to compatibility with GC versions that will only be available in FSF 14 next year. So that's the support for exceptions and non-termination. And I put two examples here of what are the exceptional cases, so specifying under which condition the program might raise an exception, and specifying when the program is expected to terminate. So many more examples in the user's guide. So very interesting developments, because exceptions and termination were kind of the last bits which we couldn't swallow, and we can now. We have added more specification features, and I list just 3. One, which is to describe what is the actual mathematical logical equality on a type, because equality in Ada is an operation. It can be quite complex. So for example, equality between arrays is just the equality of elements, not the bounds. But that makes it difficult to reason about it in provers. So if you want to have an operation that is the real mathematical equality, so nothing can be distinguished, you can use this new annotation logical equality. Another one, which is quite nice, is to be able to state that some lemmas can be automatically instantiated when they are associated to a function. So after a function, we can say that this lemma, this lemma, this lemma have automatic instantiation. In that case, the prover itself will find the actual theorem or axiom in the generated theory to instantiate whatever is needed about this function. And the last one, small one, but nice one, is that until now, predicates in Ada are used in certain ways that prevent them from using ghosts. So prevent them from using things that are only for verification. And sometimes it's quite convenient. So we have added another one of these predicate forms. So there are static predicate, dynamic predicate which summarizes them both, and the new one, ghost predicate, where in the condition you can use ghost elements. So now, very fast, going through compiler technology improvement that you could find useful. Last year, I presented LangKit, which is the base platform for lexer, parser, semantic analysis of various languages, and which we use ourselves for libLang. So an Ada, lexer, parser, and semantic analysis that we use in many different contexts. So for example, using it through IDEs, so whether Visual Studio Code or GNAT Studio. And on top of that, I presented also LKQL, so the query language associated to LangKit, which is quite compact. So you can see in a few lines how we can detect a declaration of generic formal objects of mode in-out. And what we've done this year is improve a lot the runtime of this analysis. So both the solver for LangKit, so just to get a fully analyzed abstract syntax tree, and the last version of the solver is based on DPLL of T, so the technology used inside SMT solvers. And we have a nice article at the upcoming SMT workshop if you want to look it up. And finally, the LKQL language itself was improved also a lot in terms of runtime, because now it will be compiled with the just-in-time compilation based on truffle. So also gaining many folds the runtime, dividing the runtime by a few. We added in GCC nice features for security in terms of confidentiality. So whether the code can be attacked by side channel attack or by like laser or power consumption, so these physical attacks, an attackant could take some secrets from your applications. And these measures are meant to block the attackants, and they are applicable to both Ada, C, and C++ because they are done quite low in the GCC stack. And so some of them are already available, and all of them should be available next year. So that's scrubbing the register and stack to not leave any secrets. Hardened conditional, so that the test and the negative test are done in sequence. Have redundant encoding of Booleans, and finally checking that the right control flow was applied and no branch was ignored. Very fast, because I'm almost over my time. We are progressing on our strategy to have a different backend for GNAT. So instead of GNAT GCC, we're working on GNAT LLVM, based on LLVM. The same frontend is shared, but this year we are aiming at the first 2 native targets, so 64-bit Linux and Windows. And this is used already in our GNAT for CUDA technology that was mentioned by Miguel for the device code generation. And it's also used in an internship where we have worked on an experimental WASM targets. So WASM is this language for the web, but that you can also use on any platform thanks to the technology called WASI, so the system interface of WASM. And finally, it's used in our technology called Common Code Generator that generates C from AdaSpark. I finish with analysis technologies. So a few graphics. I won't explain all that. But first testing now is well integrated in our tool chain. So you can see here various tools that you know. So GNAT Studio, GNAT, and GNAT coverage. Now it includes the ability to fuzz the software. So by very quickly changing the inputs and trying to exercise new branches. And this is based on the well-known, very popular IFL plus framework for fuzzing. Next is record flux that we announced in March. This is using the technology for formal verification that we have, Spark, in a very specific domain. So communication protocols, where a lot of the code has to be boilerplate. So here, instead of coding directly, we want to generate the code from a succinct description in a domain-specific language. So that goes both for the specification of the messages exchanged and for the session, so how those messages are exchanged. So that's the two central pieces, and everything evolves around that, in particular, the generation of Spark code, which is proven correct with respect to this specification. So if you want to know more, please look at our website, both the blog and the record flux pages. To finish, 2 minutes late, we have this new engine inside our GNAT static analysis suite, so what we called previously code pair, which is called Infer, so based on technology from Meta Facebook. And here the angle to approach bug finding is this thing called incorrectness logic. So instead of doing classical abstract interpretation, the goal here is to do an under-approximation to have only sure problems. So sure errors that someone should fix. And the first two checkers that we've developed based on this new technology that will be available in our static analysis suite soon are detection of memory leaks, which is notoriously hard to do by classic and abstract interpretation, and detection of function call with side effects when they're on the right-hand side of lazy evaluated expressions, so and then or else, etc. And that's all. Thanks for bearing with me and my 3 minutes over time.